Thank you. And thank you all for having me here, of course, in this lovely city. So does anybody write any code at all? Oh, good. Okay. Yeah. Okay, so yeah, so I've already been introduced, but my name is Riccardo LIPPOLIS. I know my last name might sound Greek, but I'm actually half Italian, half Dutch. And I think my last name is one of the many things the Romans borrowed from the Greeks. Yeah, so I live near Rotterdam, and for those of you that don't know, that's one of the major cities in the small country of the Netherlands. And I am doing whatever role involves writing code. So I'm software engineer, I sometimes do architecture stuff, DevOps, whatever you want to call it. I don't care about the title, I just want to write nice code. I've been doing Java for about 15 years now, and in the last 5 years transferred a bit to Kotlin, where I still do currently, well, mostly Kotlin with some Java in legacy systems. And I've been giving talks about reactive programming, and then I switched to Kotlin, and then started doing talks about Kotlin Coroutines. And so the next logical step for me was to start talking about virtual threads, because basically a lot of people came to me when virtual threads was being released, saying like, hey, is this like something that makes Kotlin Coroutines obsolete? How does it combine? What's the overlap? What's the differences? So I'm going to start with a huge spoiler saying Kotlin Coroutines is not going to go away. I think the virtual threads that are introduced in Java 21 are actually pretty nice, pretty powerful. And I think they're going to strengthen each other, and they both have their merits. So what I'm trying to explain to you in this talk is how they relate to each other, but also what are their differences and how you can use either one of them. So let's start with the challenge that we're trying to tackle here. As you all know, like running an application requires resources, right? CPU, memory, and those resources are finite and they cost money because, well, you have a cloud bill to pay every month and you don't want that to be too huge. So if we look at a typical Java application, a server-side JVM application that handles HTTP web requests, typically what you see is that they use a thread per request model, which means that every time a request enters the application, they get assigned a thread, and that thread is responsible for handling the entire request up until the response has been given back to the user making the request. And that thread is dedicated to that specific request. And as we know, threads, they cost resources, right? There's some CPU involved in managing these threads, and there's memory footprint involved in terms of, oh, you have some OS thread, and there's a stack size that needs to be kept, etc., etc. So if we try to visualize this, imagine we have an application here with some logic, and we have a thread pool that currently has 2 threads. And on the left, we have some users that want to make some HTTP requests, some query. And every query needs to do some HTTP call to some cloud service and needs to look up something in the database. So 4 requests, but only 2 threads. As you can see, when a request enters the application, it gets assigned a thread, and that thread is responsible for that request during the entire life cycle of the request. And you can see already here that there are some angry users. Oh, sorry. That was a bit too fast. Sorry. This button. Yeah, so we need to run it again. But these 2 users here, they are waiting until their response or their request is being handled. And there's no thread to handle their request at the moment. And you see that some threads are just like waiting here because they're, well, not doing anything at the moment. So there's some inefficiency there. So like I said, threads get blocked. There's called blocking I/O. Resources are sort of wasted because they could be doing other stuff in the meantime. And there are some scaling issues involved where basically the amount of concurrent requests your application can handle is at most equal to the maximum, to the number of threads you have in your pool to handle these requests. And for most applications, that might be perfectly fine. I mean, we've been coding like this for years, right? And a lot of applications don't have that many concurrent users, so it's fine. But there are some use cases where a server needs to be more highly available. You have a lot of concurrent users where this might become an issue. So typically, the proposed solution in that case is non-blocking I/O. Non-blocking I/O means we ditch the whole thread per request model, and we decouple the threads from the requests that they're handling and make it more dynamic. And to show how that works, same case, but now with non-blocking I/O, which means that when a request, for example, in this case, it goes to the external cloud service, and then the thread can be reused for another request in the meantime. And you can already see that users are not waiting, well, except here a little bit, because it's still, we only have 2 threads, so it's not infinite. But the whole thing goes much smoother, and users have to wait less time. So, no needlessly sleeping threads. Threads can always pick up work when they are not doing anything at the moment, but it comes with a price. There's some complexity involved here. Of course, there's more thread context switching. There's some way of coding that might be required to enable this. And yeah, it can become hard. So imagine how would you do this in Java, right? With just the plain Java standard library. You might think, oh, we have completable futures and we can chain these, etc. But yeah, we know from JavaScript that like the callback hell thing is not very nice. JavaScript solved this with the async await keywords, but Java doesn't have that yet. So a lot of people turn to reactive programming. I don't know if you've already heard of reactive programming. It was like a few years ago, it became really hot at some point, like, oh, everybody needs to do this. For example, if you were writing a Spring application, then you could switch from Spring MVC to Spring Webflux. And I actually did a talk in, well, it was 2016 with my colleague Bas. And yeah, we wanted to explain how you could use reactive programming to also be able to have non-blocking I/O. But even back then, we already had a slide in there that, yeah, there are some pitfalls. It's difficult to write, it's difficult to read. It's a whole different mental model you need to have to write these applications. And yeah, it's hard to debug as well. So yeah, we need something better. And that's where Project Loom enters. So in one of the AMAs that Brian Getz did a few years ago, Brian Getz, for those of you that don't know, is a Java language architect, so he knows everything about Java. He said, Project Loom is going to kill reactive programming. Of course, that's a very bold statement, but I think for some use cases, he's actually correct. Project Loom had the vision, the goal to be able to incorporate that non-blocking style of programming or running your applications in a way that your work as a developer doesn't get much more complicated. So have the benefits of non-blocking I/O, but not the downside of having to write very difficult, hard to debug code. So keep it low level, like easy to implement, but still have the benefits. So Project Loom consists of 3 parts: virtual threads, structured concurrency, and scope values. Virtual threads is currently the only one that's production ready in Java 21. The other 2 are still in preview mode. So you can start playing around with it, but of course, for production applications, you might need to wait for a few releases. It's not confirmed yet whether in JDK 22 they are actually going to be included as production ready, but we'll have to see. But virtual threads can be used already. So let's start with virtual threads. Traditionally, when you run your Java application, you start with a main thread, you have a main method that runs a piece of code, and maybe you start some other threads that do some other stuff. And that usually looks like, well, usually always looks like this. Your task, which can be, for example, your main method or some other runnable that you provide to a thread, gets assigned a JVM thread, which is one-on-one linked to an OS thread. So that involves some memory, footprints, some CPU to handle, and of course some OS resources as well. And each thread you start gets that same thing. However, with virtual threads, it looks like a little bit more like this. It might be a bit confusing in the beginning, but of course, I'll explain it to you. So on the right, we see the same thing we saw in the previous slide, where a main method has a JVM thread linked to an OS thread, and every runnable gets the same thing. That's pretty much the same as it was before. The only difference is that those kinds of threads are now labeled as platform thread. So it's the same thing you're already used to. Pre-Java 21, it's just called a platform thread. Same thing. Next to that, the JVM now has a pool of carrier threads, and the pool size depends on the number of CPUs you have. It's all handled under the hood for you. And a carrier thread is, in essence, also the same as a platform thread. The only thing is that it has a different use. So carrier threads are used to run virtual threads. And virtual threads are the things you see here at the top. And the funny thing with virtual threads is that it's not an actual thread. It's just, it has the API of a thread like you're used to before Java 21. So you can just create that, pass a runnable, and then it runs your code. The only difference is that it runs only on these dedicated carrier threads. And as you can see with the lines here, they are not confined to a single carrier thread. So a carrier thread can run multiple virtual threads, and a virtual thread can theoretically be run on multiple carrier threads. So you see the disconnect between the task we're doing and the pool of threads we're working on. And that might ring a bell from what we saw before with the non-blocking I/O, right? So imagine we have two virtual threads, two runnables, two pieces of code that we want to run. How do they both run on one carrier thread? So in this case, I just took one carrier thread, but in practice, there are, of course, more. So imagine we have a virtual thread 1 that starts running some code. And, well, because the carrier thread is available, it can use that carrier thread to run that code. And at some point, it does some I/O call, for example, a database call or a HTTP request, and it has to wait for a response. So virtual thread 1, during this period, is waiting for a response from some external entity. At that point, the virtual thread cannot continue. So you can say it's like parked or suspended or whatever you want to call it, but basically it's paused for execution. At that point, the carrier thread becomes available to do other stuff. So in this case, virtual thread 2 wants to run some code, and well, the carrier thread is available, so it can run on that thread. Whenever the response from the external entity returns and there's no carrier thread, of course, there's a small window in which you have to wait. You know, like I said, you cannot like infinitely run everything at the same time. There are still limits to it. But the moment virtual thread 2 pauses or suspends, virtual thread 1 can finish its work, and then in the end, virtual thread 2 can as well. So you can see how they get like intertwined on the same thread. So when does a virtual thread suspend or pause or whatever you want to call it? Well, basically every blocking call that's in the Java library is converted to be able to support virtual thread suspending. So think like reading from a stream, writing a stream, reading from a socket, sending something to a socket, but also some like lock mechanisms you have where you can wait for a lock to be released. All these methods have been made compatible with virtual threads, meaning that if they run on a virtual thread and they get to that blocking point, the virtual thread is suspended and some other virtual thread can run on that same carrier thread. There are a few exceptions. So if you have a synchronized block of code, so you know the synchronized keyword from Java, if something blocking happens within a synchronized block, then the virtual thread will not suspend to prevent deadlocks. So if you have that piece of code where you do some blocking stuff within a synchronized block, you can rewrite that to use the Java util concurrency lock mechanisms, which do support it. And if you do something with native methods or foreign functions, I've never encountered anyone actually using it, but there are a few people using that, so keep in mind if you're using that, when you call a foreign function or a native method, then it will not suspend your virtual thread, again, to prevent deadlocks. So use cases for virtual threads, well, the thread per request style server applications, as we saw before. Basically, enabling virtual threads converts your blocking I/O application into a non-blocking I/O application without any additional effort. Well, almost no extra effort, which is cool, right? And if you have like some highly concurrent I/O-bound code, you can use virtual threads to speed that up as well. But keep in mind, the virtual threads are not making your CPU-bound code run faster. So if you do some calculations and you do them on multiple threads to do parallel calculations, virtual threads are not going to help with anything there, because it's the same as running that on a normal thread pool. There's no difference there, except that you're like blocking all the virtual threads from doing I/O stuff. So for computations, just keep using normal threads there. So creating virtual threads is very easy. Like I said, you can just start a virtual thread like you start a normal thread. You pass a runnable, that's just a block of code, and it can be started. And you also have the possibility of creating an executor, which creates a virtual thread for every task that gets submitted to that executor. The important thing to remember is it's not you should not pull virtual threads. Virtual threads are really for one-off tasks. Just create them, they run your runnable, and after that they are disposed. That's the whole idea. They're lightweight. They can be created on demand, and when they are no longer needed, they get cleaned up. Because a virtual thread, the stack of the virtual thread is stored on the heap. So it just gets garbage collected like every other thing on the heap, when it's no longer needed, of course. So do you get better performance with virtual threads? Well, like always, it depends. I mean, I'm a consultant, so I have to say it depends. If you're interested in learning whether or not this helps your application, I would say just try it out, measure, do some performance tests, see if it helps you. It really depends on the use case. If you're interested in some numbers or some other talks on how virtual threads performs compared to normal threads, I would suggest these two talks. The one on the left is Mark Thomas. He's from the Apache Tomcat application server. He's a contributor there, and he has done some very low-level tests on how it performs compared to the normal threads. And he also explains the difficulties they had with Tomcat to make it compatible with virtual threads, so that you can just enable it with a flag and everything works, but they had to do some work underwater or under the hood to make it work. For example, they had these long synchronized blocks that I was explaining earlier, so they needed to do some work there. And if you're interested in a more lighthearted talk, I can recommend the one on the right, which is Mario Fusco. He implemented the game of life using virtual threads, where every cell of the game of life is a virtual thread communicating with other cells. It's fun how that works. Moving on to structured concurrency. So as we all know, concurrency is hard. It's hard to write good concurrent code. It's hard to reason about it. It's hard to debug in some cases. But in the end, we do sometimes want it, right? So talking about the reasoning about code, if you have sequential code, and of course, because I'm half Italian, I involve cooking pasta, but if you have a recipe and you write it in a sequential way, so single-threaded, it might look something like this. Just by reading the code, you can already reason about it, right? Just because we know how imperative-style programming works. So we know that the serve dish function will only be called when the prepare dish function has returned a dish. And within the prepare dish function, we know that we only return a dish when we actually call the other two functions. So it's very easy to reason about it. We understand when an exception occurs at some place within the code. We know what has been run and what hasn't. So what if I told you we can do the same thing, but with concurrent code? So again, the same example, but using structured concurrency. There are a few things added here. Of course, because it's Java, it might seem a bit like convoluted if you're really used to like the Kotlin style of programming where everything is like nice and clean. But I mean, it's an early implementation of structured concurrency, so it will surely improve over time. So what we see here is that the prepare dish function now is run in a thing called a structured task scope. So we see on this line that we create a structured task scope, and we use the Kotlin extension function called use. For those of you that are not that familiar with Kotlin, it's basically like a try with resources block. So at the end of the use function, when this block of code has been executed, the resource is closed. So the structured task scope is closed. Don't be too frightened by the shutdown on failure. It's not a JVM shutdown. It just means shut down the scope in case one of the tasks fails. So you have an alternative that says, well, shutdown on success, which basically means return whenever I have some result from one of the concurrent tasks that I use. But I think shutdown on failure is the one you're usually going to need. So we want to make the pasta and the sauce at the same time. We want to do that in parallel. So in this case, we can use the scope variable that we got to fork processes that do something in a separate thread. So in this case, we have two tasks that we do in parallel. And when they are both done, and we check whether they actually are returned successfully and don't have any exceptions, we can get the result from those tasks and return the dish. So in this case, we have concurrency, but we get some guarantees which enables us to reason about this code easier. So we know that within this block of code, this block will only return when both the pasta and the sauce are done, but we can still do something in parallel. So we don't have any dangling threads or runnables, tasks that are forgotten to be cleaned up, or so it's easier to reason about this. So like I said, it's still an early implementation. It's a very basic functionality. By the way, it's not limited to virtual threads. By default, it uses virtual threads, but you can pass another thread factory or thread pool so that it uses that instead of virtual threads. And the idea is to make it extensible for like third-party libraries, and in the future with new JVM releases, new functionality will come as well. So the final thing, scoped values. They enable to share data within and across threads, but in a scoped way, again, to prevent leakage to parts of the code where you don't want it. So imagine we have a principal object or authentication object which states, okay, which user is currently logged in and which rights does this user have. We can configure a scoped value of a type principal, which can be whatever, but in this case it's principal. And then within a block of code, we can define the value that scoped value has within that block. So in this case, we say scope value.where. We pass the scope principal, and we say in this block of code, I want the value to be normal user. Which means that when we do some normal user stuff, and that function checks if the logged in user is actually the correct user, so is it a normal user, it can get the right value. Which also means that if you call scope principal.get anywhere outside of this block and it's not defined, then it throws an exception. So this value will not leak outside of this block of code. And the nice thing is you can also override the value in a child block of code, you might say. So in this case, when we want to temporarily elevate the right to administrator to do some administrative actions, we can do that. And within this block of code, we get the right value. So a pretty easy way of working with those kinds of values. I might hear you think like, yeah, but I mean, we have thread locals for this, right? So yeah, we can still use thread locals, even with virtual threads, because the good thing is that thread locals, they are bound to virtual threads. So basically, they work the same as you're already used to, except that there's a downside when you're using thread locals to store sort of like a cached version of an object that is expensive to create. So sometimes some libraries and some applications use thread locals to store objects that are expensive to create and maybe are like not thread safe. They store them in a thread local. so that they can be reused whenever that thread is doing some other task. But in the case of virtual threads, of course, they get cleaned up every time. So that means that they get created a lot more. So if you have those kinds of use cases, it's better to use something like a resource pool of those objects or something else. But for simple passing of context, maybe a transaction context or a security context, they can still be used. So for the people familiar with Kotlin Coroutines, I think a lot of these terms are already, like, they ring a bell. Because, I mean, Kotlin Coroutines has suspending functions. They also have structured concurrency. And of course, they have like the concept of a coroutine context. So how do they relate to each other? Well, in a lot of ways, they are pretty similar. So if we look at suspending functions, if we have multiple coroutines running, they can all run on some dispatcher thread, which is a thread provided by the dispatcher that you're using. And it's the same as with virtual threads. The same principle applies here. Whenever it suspends, another coroutine can continue on that thread. But there are some differences there. The implementation of suspending functions in Kotlin is, of course, on top of the JVM. Because, well, Kotlin is like multi-platform, and when Kotlin introduced suspending functions, it was not available in Java. So they basically built their own implementation of suspending functions on top of the JVM, where virtual threads are configured within the JVM. With coroutines, you can define your own suspension points, so you can create suspending functions which suspend whenever you want, where with virtual threads, it's confined to whatever the JVM provides for you. So the Java language functions that have enabled virtual threads are the only places where they can suspend. And of course, the dispatching. With coroutines, you get to decide the dispatcher you're using to run these coroutines. So you want to run it single-threadedly or multi-threaded in the pool or like unbounded, however you want it. Where with virtual threads, it's just carrier pool only, and you have no control over it except when you do some JVM hacking, which of course we don't do. Structured concurrency is pretty much the same idea, just looks a bit more neat in the sense that you can use coroutine scope to create a scoped block of concurrent code. And yeah, I mean, I like this better, of course, because it's more compact, but with some clever Kotlin extension functions, you can reach the same thing with the Java structured concurrency, of course. Regarding the coroutine context, I think, yeah, if you think back at the scoped value, it's a pretty similar idea, right? The principal context we have here, which is our own custom coroutine context element, can be used in the same way as we used scope values. Only in this case, I like the scoped value approach better because it's like less code, but it's one of the few points where actually the Java code is smaller than the Kotlin code. But the same principle applies. You can override the value within a certain context, and within a child context, you can override the value again. So same principle. So yeah, we have virtual threads versus suspending functions. We have structured concurrency in both of them. We have scope values versus coroutine context. So it's all pretty similar, right? So what are the big differences between the two? Well, there are a few. One of the things is that the fundamentals of the way it works is pretty different. So in Java, it's pretty much implicit. You transparently get virtual threads enabled if you want it, and the methods you have are implicitly suspending. So you don't need to customize the function to make it suspending, but just because the JVM handles it for you, it's automatically suspending if you run it on a virtual thread. So there's no difference in how you write your code. Where with Kotlin coroutines, it's pretty explicit, right? You have to write suspending functions. You have to write it yourself. You have to think about which functions need to be suspending, which don't. So it's more explicit and it requires more reasoning about it. So if you ask me which one is better, I think that's a matter of personal preference. Brian Getz from the Java community, he prefers the implicitness, where the Kotlin people prefer more the explicitness. If you're interested in some theory behind this, I can recommend the blog article, the link here, which is called "What Color is Your Function?", which kind of explains this principle, like what it means if you have to explicitly separate between async and non-async code. But in this case, he talks about JavaScript, but the same principle applies here. So use cases for virtual threads and Kotlin coroutines. Well, with coroutines, we can do asynchronous computations, we can do asynchronous UI, we have the principal futures, which are called deferred in that sense. We can write sequence generators, we can do channel-based concurrency, actor-based concurrency. There's like a lot of stuff in there already. With virtual threads, well, we can write IO-bound JVM applications, and that's it for now. So in terms of use cases, Kotlin coroutines provides a lot more at the moment. But I mean, it's a bit of an unfair battle because coroutines has been around for a while, right? Target platform, well, as you all know, Kotlin is multi-platform, so it can run coroutines on all the different platforms, where, of course, virtual threads is JVM only. So a lot of people ask me, so can we combine virtual threads with Kotlin coroutines then? I mean, if they're both like powerful concepts. The answer is, well, yes, but think about what it provides you, actually. I mean, it's something that you need to measure if it provides any benefit for your application. So theoretically, what you can do is what I did here was create a virtual thread per task executor, so a JVM executor that creates a new virtual thread for every task that gets submitted, and I convert it to a coroutine dispatcher, and then I can just run my suspending functions on using that dispatcher, and whenever within that dispatcher I do some blocking IO function, so a traditional blocking function from the JVM, it gets suspended as a virtual thread instead. So you get non-blocking both in your coroutine code and in your traditional JVM code all in one. However, I have to say that the coroutine library creators did a fantastic job of optimizing the coroutine library to work with normal threads. So they haven't done any specific work to support virtual threads yet in a way. And so keep in mind that it might not be the way that they're supposed to work for you. So as always, measure, measure, measure. So what now? The reactive high-level concepts, they still apply. I mean, non-blocking I/O is a nice thing, and the whole thing about reactive programming, about it like creating scalable systems which are resilient, etc. They're all good concepts. So if you have an application that's written like that with a reactive library and with those principles in mind, you don't need to change everything up and like convert it to a traditional web application again. You can still use it. However, if you're starting a new application or you have an existing traditional JVM application, then instead of switching to some reactive library, you might think it's a better way to just start using virtual threads instead, to see if that provides you any benefits without having to redo all your code. So you can still benefit from non-blocking I/O, but don't incorporate the whole reactive framework. And if you're doing Kotlin coroutines, yeah, you can just keep using them, as I've tried to explain in the slides before. It's still an awesome library, and it still provides a lot of benefit in a whole range of use cases. And if you want to start with virtual threads, yeah, go ahead. It's production ready, so you can start using it. The future of Loom, of course, it's a bit like hard to know where it's actually going, but I have some expectations. We already see that virtual threads are being adopted by the major framework library developers. For example, Micronaut already supports it, Quarkus, Spring Boot, starting from Spring Boot 3.2. You just have to enable a flag, and it will start using virtual threads if you're on JVM 21. So it's really easy to start using it if your libraries are up to date. The structured concurrency constructs, I think they will improve over the time. I think for now it's like it still has some limited use cases, but I think library creators will start building upon it, and Also, the JVM will keep expanding on that part as well in future releases. And maybe we'll eventually see other Kotlin coroutine-like constructs. So maybe at some point, sequence generators might be an option in JVM as well. Might be cool. And maybe even the internal Loom API might be opened up so that we can write our own suspending functions on the virtual thread, which currently isn't planned yet, if I'm correct, but it might change in the future. So that might provide us with new ways of writing cool applications. So with that, I would like to thank you. And I think we still have time for questions, if there are any. I see a few. I don't know if there's someone in a microphone or. Can you raise your hand again if you have a question? No.
Hello. Yeah, I would like to ask you about, first of all, two questions about the virtual threads. When you write code that is supposed to run on virtual thread, do you still need to synchronize it to treat it, let's say, as a code that runs on different platform threads? That means you still need to do typical multi-threading stuff, which is usually complex. And the other question about reactive programming, one of the good things about reactive programming is that it also supports back pressure. Can you achieve something like that with virtual threads?
Good questions. So the first question, do you still need to do manual synchronizing when you're running multi-threaded code on virtual threads? Yes. So synchronizing, of course, try to prevent using the synchronized keyword for long-running blocks of code. So using purely the synchronized keyword is fine. Just don't try to block the carrier thread for too long. So if you have like a small block of code that needs to synchronize, that's still fine. Of course, if you can use the new concurrent lock mechanisms that are provided by the JVM, that might be even better, might be more performant. But in essence, synchronization is still a thing you need to keep in mind. The second question was about back pressure. If you're dealing with back pressure, there are currently no out-of-the-box mechanisms except like using a queue, like a blocking queue. You can like implement it for yourself, but on those fronts, I think the reactive libraries already have done a lot of work, which of course might be easier to use if you're specifically looking at back pressure.
Thank you.
See, there are two questions.
So, as you mentioned, suspending functions are built on top of the JVM, while in contrast, virtual threads are built in the JVM. So does this mean that performance-wise, we should be using virtual threads for stuff that can be done with either of them?
Good question. Again, consultancy answer, it depends. So the thing is, the way they are implemented differently means that Kotlin coroutines basically sort of are cheap to suspend, but they have some overhead when they reach a suspension point but don't suspend. So that means that code that doesn't suspend that often will technically, well, in theory, run faster on virtual threads than on coroutines. But the difference is when a virtual thread suspends, then it needs to copy basically the current stack to the heap. So there's some overhead involved there. It's such a low-level thing that it's hard to say which will perform better in your application without knowing the use case. But the way the Kotlin coroutines are implemented on top of the JVM is basically that if you write a suspending function, it turns your suspending function into sort of like a state machine, where every state transition, meaning every point where it could suspend, it basically saves the current state of your method. So if it needs to suspend, basically it already has the state, so it can suspend quickly. But if it doesn't suspend, it saved the state for nothing, basically. You know? So it depends. But are some differences indeed in performance between the two.
Okay, thank you.
Thank you for the presentation. Do you think Java virtual threads would get in the future more customization capabilities, at least some, like coroutines have?
I hope so. I did read some things about it that they don't have any plans at the moment to do it, but that might change in the future, and I hope it does. But it's hard to say if it happens. They haven't planned it yet. That's the short answer for now.
Hello. I want to ask, what is the stack size of a virtual thread? Is it equal to a platform thread? It's a half one?
Also a very good question. So the stack size, like for normal threads, it's about like default 1 megabyte, and usually people reduce it. For a virtual thread, it's in the order of magnitude of bytes. So it's like really cheap. Except, of course, the objects that are on the stack or on the like your local variables, etc. So the objects involved that differs, of course, per use case, but merely the virtual thread itself and the overhead is like really small, like a few, I think it's a few hundred bytes if I'm correct, like very small compared to a normal thread. Yeah. See one more question. We are a bit out of time, but maybe you can still.
Hi.
Hi.
You said before that with virtual threads, we don't need pools, thread pools, and stuff like that. But the thread pooling is not about only to have a heavy thread vs a light virtual thread. Most of the time, we are making queries to databases, and we like to throttle the sum of parallel queries go to the database. So if we want to have a thread pooling, we don't have throttling. So we maybe have 1 million queries to the database. This cannot happen. So what will we do in this situation with virtual threads?
Also a very good question. So I want to nuance a little bit. The virtual threads themselves don't need to be pooled, but you can still have thread pools outside of virtual threads, of course, that's the first thing. But indeed, excellent question, like if you have 1 million virtual threads all doing database calls, then yeah, you don't want that because your resources are limited, right? So in that case, I would prefer like keeping your a database connection pool sized to up to a certain point, and then basically getting a connection from that connection pool would be sort of like a blocking call, like waiting for a connection to be available, so that at most, if your connection pool has like a size of 10, you would have at most 10 concurrent requests to your database. So indeed, it doesn't mean that you want 1 million requests going to your database at the same time. Does that answer your question? So yeah, so let's phrase it differently. You still have to limit your resource usage, but you cannot do it based on a thread pool in case of virtual threads. You need another way of limiting it. That's in essence the answer. So if you have in terms of database, you can use a database connection pool with a maximum size. If it's some other resource, you can use another resource pool, but you have to limit it in some way indeed. Thank you.